Certainly nobody brought this to my attention, but I forgot to put up an assignment already this week. And maybe you just wanted to keep quiet about it and hope that I didn't put one up. I would like to do something for the Electrochem chapter. It's too late for me to give you like a full-on assignment. How about a short one? I got one nod and nobody online can respond easily. Can in the chat. If you have strong feelings about that, let me know. I think you have a midterm next week in calculus, or is it in physics?
I like it, and then
so you're not in either, yeah. Yeah, just let me know. Maybe what I'll do is this. I'll make an assignment and it'll be optional. So if you need a break, or if like just your life is crazy, or you have a midterm or whatever, and or you just don't feel like it, you can skip this one and there'll be no penalty, you know. But if you do it, you can use that to replace a different one. It's kind of like a bonus. That makes sense? I'll think about that just a bit more and I'll make it clear when I send the email out. Calc and bio midterm. It'd be nice to have the optional assignment for practice. So yeah, I will definitely put one up that'll be optional, but it'll be a bonus. So it's not like if you do it, you'll get no value for it, right? It can still count. I've been actually working in my lab on developing a lab for you people in this class. And it involves, actually, I was visiting a friend a few weeks ago, and he let me know he's a coin collector. And apparently dimes in Canada prior to 1967 were made of 80% silver. So like in 1966, the Canadian dime was 80% silver and 20% copper. And a dime weighs roughly 2.5 grams. So, you know, you can do the math there. It's roughly 2 grams of silver in one dime. And if you actually work out what silver is, it's like $1.25 or so, just in terms of the pure silver value. So if you have a giant coin collection of like random change, go through and see if there's any dimes older than 1966, because they will have more value than anything produced since then. So my idea for a lab was to take one of these dimes and refine it, meaning we're going to turn it from 80% silver to 100% silver. And I can show you the chemistry behind it. Sometimes writing it down on paper and doing the chemistry can be two very different things, because of course, one other important factor is rate, which you can't always control and has to work in a 1 hour period. But what you can do is if you took one of these dimes and reacted it with nitric acid, what happens is you have two reactions that take place. You have the silver part reacts with HNO3 and it makes H2 gas. So I guess we're going to need two of these, plus 2 silver nitrates. And if you do the same thing with copper, it will react to make hydrogen, which is a gas, plus CuNO3 to aqueous. So you drop the dime in, the nitric acid, it bubbles, and that's the hydrogen gas being evolved from both of these metals that are in the coin. And at the end, what you have is a solution that contains silver nitrate and copper nitrate, both of which are completely soluble in water. According to our solubility rules, all nitrates are soluble. So in solution, you have silver plus, you have copper 2 plus, and then you have a bunch of nitrate in there. So what you want to do is get the silver out while leaving the copper 2 plus behind. And there's a couple methods to do this. One is if you just take a coil of silver metal, so if you take like silver wire and turn it into a coil and drop it into the solution, That won't work if you just drop the copper coil in because it'll dissolve as well because there's still nitric acid left in there. So what you need to do is take this solution and neutralize it with NaOH. You have to pick a base that's not going to precipitate anything here. And silver will precipitate with almost anything. So silver will precipitate as silver chloride, which is insoluble, so you don't want to add anything with chlorine in it or chloride in it, iodide, bromide, all kinds of things like that. So if you neutralize it, then add a piece of copper wire, you get a reaction where the Cu solid will react with the two silver pluses, and this makes 2Ag solid plus Cu2 plus. So the copper dissolves away. This is like a typical, this is a spontaneous reaction. This would be like a typical reaction that you might do in an electrochemical cell, but split into two halves. But you can throw it all in together and it'll work. The reaction is not instant, right? This reaction would take a while. But what you could do is pull out the piece of copper at the end, shake off any silver or scrape off that's attached to it, take your silver, filter it off, and then melt it down into a little silver ball. So you can do it that way. Another way to do it is if you have the silver plus, another thing you can react it with is sugar. And that will, I don't even know what the sugar gets reduced to, but many sugars are called reducing sugars and can give up electrons to things like silver plus. But whatever it is that it turns into, it remains in solution. So the advantage of using sugar over copper to reduce the silver is that sugar is, you can put it in the same phase as a silver plus. It can be dissolved in water, which means you can put a huge excess of sugar if you want, which would increase the rate, because we know that the rate is a function of concentration. The other thing is when it is in the same phase as the silver plus, it's easy for them to mix. It's easy for them to collide. Whereas if you have a piece of copper wire, reaction can only take place at the surface of the metal. And that slows down your reaction because there's only a very limited kind of amount of real estate that allows the reaction to take place. But my hope is I can kind of get these kinks worked out. And at the end of the day, you should be able to walk home with a little button of silver, which would be worth $1 or so, right? But anyway, you can brag that you purified it yourself from an old Canadian coin. So I have the coins. I've done. It turns out you have to be very careful with the neutralization step. That's the part that's giving me trouble, because if you overdo it and add too much sodium hydroxide, that will precipitate the copper as well, and you get copper hydroxide solid, which is like a blue powder, and it's really fluffy and it'll fill up the flask. And you need to have just the right amount of acidity, because too acidic and this silver that's produced will redissolve, and not acidic enough and the copper will precipitate. So you've got to just get it in the right sweet spot there, which I was pretty sloppy in my first attempt, so hopefully we get there. All applications of electrochemistry, right? We know that the reduction potential of silver is higher than the reduction potential of copper, which allows that copper-silver reaction to work. Okay, so we spent quite a bit of time looking at electrochemical cells, how to build them, how to do the line diagrams, all that kind of stuff. We learned about reduction potentials for half reactions and how you can put them together to get a cell potential or a cell voltage or an E0 cell. We also looked at the E0 cell, and we were able to use that number to determine if a particular electrochemical cell would be spontaneous in the reaction written or non-spontaneous. And we said if a cell reaction had a voltage above 0, then it would be spontaneous. If it's less than 0, it'll be non-spontaneous. And you might remember, like we use similar sorts of things when we talk about delta G. If delta G is negative, we say it's spontaneous. If it's positive, non-spontaneous. Or if the equilibrium constant is above 1, then we would say that that equilibrium, if it's in standard conditions, it would be spontaneous for it to shift to the right. And if it's less than 1, it would be spontaneous for it to shift to the left. So really, these three different measures, the voltage of the cell, the delta G of a reaction, and the equilibrium constant for a reaction, all three of these are really all telling you the same information. They're telling you the spontaneity, and they're telling you the driving force for this to shift to the right or shift to the left. So really, you can kind of think of these three things as being more or less the same. Like obviously they're not going to be the same number, but they're all conveying the same information. There's a relationship between them, all of these three things. They're all telling you the magnitude of the driving force for a reaction to go forwards. So, you know, this is all derivation here, which is great. You can look at it, but I'm going to cut to the chase and show you the relationship between the E0 cell and the delta G0 of a reaction. And the relationship is a very simple one. Delta G0 of a reaction is minus NFE0 cell, E0 cell. I guess it's E0 cell, it's not E0, because E0 would be if the little circle was subscript, which is not what it is. F is a constant, it's called Faraday's constant, and you can see it right there. It's basically the electrical charge found in a mole of electrons. It's 96485 coulombs per mole. So that's just a constant. And N is the number of electrons that are transferred in the electrochemical reaction. So remember when we do these electrochemical cells and we come up with the half reactions and we have to multiply potentially by factors to make sure that the electron number on both sides is the same, then we add them and we cancel. Whatever that number of electrons was that we cancel out, that's the N value here. And that's important because when you do an electrochemical cell reaction, you could like double the entire reaction, you know, multiply all the coefficients by 2, and that does not change your E0, but it does change your delta G. So that N accounts for that. So if you double it and you double electrons moving, yes, that's going to double your delta G, but not change your E0 cell. So straightforward equation and very useful. Okay. If you're under non-standard conditions, meaning you're not at 1 molar or 1 bar, you can use this form of the equation as well, which is the same. It's just the little zeros aren't there. You're not under standard conditions. So let's look at an example. Okay, here we have a question. It says use standard electrode potentials to calculate the standard Gibbs energy change at 298. The standard Gibbs energy change is the delta G0 at 298 for the following reaction. And the 298 is important because all those electrode potentials, those reduction potentials that you find in the tables are calculated at 298 degrees. Okay, so looking at this, we have two half reactions. We have the aluminum, 2 aluminums going to 2 Al3 plus. And if you want to know how many electrons are moving here, you just need to balance the charges off. So we need 6 electrons here because we have 2 times 3 plus. The other half reaction is 3 zincs. And that's reacting to make 3 zinc solids, and it's got 6 electrons here. So if you add those two together, you get the result that you see here. And the reason the 2s and the 3s are there is so that the electron number that's moving is equal in both half reactions. Great, so what does that mean? Well, 6 electrons is N. Okay. So I'm going to run out of space here pretty quick, but what we need to do to find delta G0 minus NF E0 cell. We know F because it's a constant. We know N now because it's 6. We figured that out from our half reactions. The remaining piece of information that we need is the E0 cell. So we could say that our E0 cell is our E0 cat minus E0 N. And we have the zinc half reaction and the aluminum half reaction. Which one of these two half reactions is the cathode? Cathode is where the reduction takes place. The reduction means it's gaining electrons, and the one that's gaining electrons here is the zinc. The zinc is going to be our cathode, so we find the zinc reaction, and we find its E0 value, which is negative 0.76 volts. And now we have to subtract from that the E0 of the anode, which is the aluminum going to aluminum 3+. And we see that one right here, aluminum 3+ plus 3 electrons to aluminum, and it's negative 1.66. And when you calculate that out, you get positive 0.90 volts. Okay. Now notice, the half reaction that's written here and here doesn't have the 3 or the 2 in front of it like we have in our balanced equation over here, 3 and the 2. But that doesn't mean, because there's a 3 and a 2, we don't do anything to the E0 value from the table. We don't multiply it by a factor, we just leave it. And that gives us our voltage. Okay, so this is actually very straightforward. We don't have to worry about stoichiometry when we use these E0 values to calculate the E0 cell. Notice as well that the E0 cell here is a positive value. So what a positive value means for us is this is going to be, we would expect this reaction as written to be spontaneous. Right? So that means the delta G0 we expect to get at the end, we expect to have a negative value because negative delta G means spontaneous. Well, let's finish this off. Delta G0 equals minus NF E0 cell equals minus 6 electrons, no units because it's just a counting number. F, which is 96485 coulombs per mole, times the E0 cell, which is positive 90 volts. You work that out, you get a number equal to negative 5.21 times 10 to the 5. And our units here is like coulombs volts per mole. It's kind of a weird unit, but it turns out a coulomb volt per mole is the same thing as a joule per mole. Coulomb times a volt is a joule. (10 to the 5 joules per mole equals minus 5.21 times 10 to the 2 kilojoules per mole. You can leave it in joules, doesn't matter. It's not like one's right and one's wrong, but we have this number. It's good. It's a negative value, which is great because we predicted already it would be spontaneous. So everything's kind of working out here pretty good. So we need to know what N is. We need to calculate E0 cell. Then we just need to plug those numbers in and get our delta G. But just remember, a coulomb times a volt is equal to a joule. This is an important factor. All right, so another example here listed as homework. So if you guys want to try one on your own, please feel free. Okay, so we related already E0 cell with delta G0. We know that delta G0 is also related to K. And we have the equation delta G0 is minus RT ln K. Well, if delta G0 is related to K by this equation, then we can also relate E0 cell to K by an equation as well. So just rearranging the equation with delta G0 and also substituting in the fact that delta G0 is minus NFE0 cell, we can arrive at this form of the equation. So just by pushing those two previous equations together, rearrange just a little bit, get rid of the two negatives, and you have the natural log of K is NF over RT E0 cell. So this is another way we can convert for an electrochemical reaction the equilibrium constant for that reaction with the E0 for that cell. So we know how to count N now. F is a constant, R is a constant, T is whatever the temperature is, and we know the other two values as well. So this is another valuable form relating to, very fundamental concepts. One in equilibrium, one in electrochemistry, and delta G in thermodynamics. So all these chapters that we're doing are actually very closely related to each other in terms of the concept of spontaneity or driving force for a reaction. All right, we know all this stuff. Good, 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 good. So let's do an example. What is K at 25 degrees Celsius for the spontaneous cell made from the following half reactions? Silver plus 3 minus goes to silver solid, right? So this is one of the reactions that we want to do to get our dimes, our money back out of our dimes. And then we have iron 2 plus reacting with 2 electrons to go to iron solid. Now, this isn't giving us a balanced equation. It's not telling us what's being oxidized or what's being reduced. We're just given 2 reduction potentials, and we're expected to pick out which one is going to be the cathode. Adrian asks, would you be able to do Q with non-standard E cell, or does it not work like that? It definitely does work like that, and we're warming up to that. We're going to get there very quick. The equation that uses E cell without standard conditions and Q is called the Nernst equation, and we're going to be arriving at that before the end of the chapter. Okay, so we have 2 reactions here, and we want to pick out which one is going to be the cathode. This is the easiest part. The cathode is going to be the one that is a greater positive value. And so we know this one is going to be the cat. It's going to undergo reduction. It's got a high reduction potential. If you mix these all together, that's going to be the spontaneous direction. And this one is going to be the anode. So we can calculate our E0 cell. E0 cat minus E0 anode equals cathode we decided was the 0.80 volt value minus negative 0.44 volts equals plus 1.24 volts. So really, there's only one way to do this. If you got it wrong, like if you pick the wrong one as the cathode or the anode, you get the same number, just the negative value. So if you end up with a negative E0 cell, you know you picked the wrong order because that would be a non-spontaneous reaction if it's negative. So we're good. We have our E0 cell. Now what we need to do is get K, and we know the equation, natural log of K is equal to NF over RT multiplied by the E0 cell. Equals, what's the number of electrons in the balanced equation? Well, if we multiply the silver one by 2, and we flip the iron one and add them together, the electrons are going to cancel, and there will be N equals 2. 2 electrons in the balanced equation. So that equals 2,96485 coulombs per mole times R, which we always use 8.314 joules per K mole. Temperature, I think we have 298 degrees. Don't forget to put temperature always in K. Multiplied by E0 cell, which is 1.24 volts. Now you see here we have coulombs times volts on top, coulombs times volts on top. On the bottom we have joules, and we said a coulomb volt is a joule. So that means the Coulomb volt is going to cancel with joules in the bottom. We have per mole on top, per mole on bottom that cancels, and we have K and 1 over K that cancel as well. So if you've set this up correctly, all of the units should cancel out on the right, which is great because our value of K at the end of the day needs to be a unitless value. Okay, so if you run that through your calculator, you will get 96.6, just a number. That's it. So there's no units. All right, so that's ln K. We want K. So E to the ln K equals just K equals E to the 96.6. And that's actually a very large number. That equals 8.7 times 10 to the power of 41. So that's a gigantic equilibrium constant. It's huge, meaning that this reaction is going to strongly favor pushing to the right. Very spontaneous, which makes sense because we have a very large positive E0 cell. So that's also suggesting this is going to be spontaneous. This might be a reaction where we wouldn't actually consider it really an equilibrium. It goes so far towards products like 99.9999999 with like, I don't know, 39s. So we would say for all practical purposes, this reaction goes to 100%. Certainly to 2 sig figs, it goes to 100%. Cool. A homework question, basically the same sort of thing. If you want to try this one out, the solutions are provided in the notes part of the slides underneath. Great, so keep this in mind. We have a relationship between these 3 measures, and we have an equation which relates all 3. This one we've seen in a previous chapter, and now we have these 2 new ones that we're adding in this one. Perfect. Great. Talked about that already. This I don't want to talk about too much. We did mention this already when we were going through the delta G chapter, or maybe it was the equilibrium chapter, but we kind of looked at a reaction as being, you know, if you're at standard conditions, kind of like delta G equals 0 when you hit a minimum, where what we're looking at beforehand or up till now is always under standard conditions. Standard conditions is a great starting point because it standardizes everything. We know exactly what we're dealing with, and we can come up with constant values for things that we can then publish in tables. But rarely in the real world are we dealing with standard conditions. And so we kind of need to understand the difference between the standard conditions and real conditions. So you could have a reaction like this one. Okay, in this particular reaction, we'll call it A. If you look at the G0 at the beginning and the G0 after, this would give a delta G value that's less than 0 and therefore a spontaneous reaction. That means if you started with everything pure as 1 bar or 1 molar, it'll spontaneously push to the right and it'll produce products. That'll change as soon as the reaction starts. You're not under standard conditions anymore, and you're kind of like sliding down this hill here until the concentrations are such that your delta G is equal to 0. And at that point, you stop moving. We say we're at equilibrium, and for an electrochemical cell, we would say that the battery's dead. Okay, we've reached equilibrium. There's no driving force anymore. This is the same situation, except this would be one with a delta G that is greater than 0 or non-spontaneous in the forward reaction, but spontaneous in the reverse. The last example we did where the K was like 10 to the 41, that would be like a reaction where it was like, you know, the minimum is so hard up against the products that it's basically just like straight line down that way. Okay, we don't need to talk about this. Concentration dependence. So this is getting to Adrian's question, what about Q? What about non-standard conditions? How do we deal with these in electrochemical cells? what does that do to the voltage if you pick other concentrations? So yeah, if we vary away from these standard positions, conditions, what can happen? So we know that there's a correction for delta G. We looked at this in the previous unit. We said that delta G0 is under standard conditions, and then we have this correction piece that we can apply to tell us what the correction factor is, the fact that we're not under standard conditions. It's RT natural log of Q. So whatever the real concentrations are of the products and reactants, you push them into the Q, and then you can calculate what the real delta G is at a specific point in a chemical reaction, if you know the concentrations. You can think of it as the delta G at any point in time is just the standard delta G plus a correction. Okay, and the correction takes into account non-standard temperatures and non-standard pressures and concentrations. So this is kind of ugly because it's on top here. But if you take the delta G 0 equals minus NFE and stick them in there, what you can do is do a substitution and come up with this particular reaction. So this is just putting together existing equations we already have, which tells us that the E of a cell under non-standard conditions is the E0 of that cell under standard conditions with this correction factor. This would be the standard. This would be the correction. It's a negative RT over NF natural log of Q. And the derivation you can go through if you don't trust me, but believe me, that is the equation. And that's called the Nernst equation. I guess probably the person who cooked it up, his name was Nernst. I don't know who Nernst was. Not an electrochemist. So yeah, this is for when you're under non-standard conditions. So let's look at an example. It says find the cell potential of a galvanic cell using the following half reactions at 298. Cadmium plus 2 electrons and tin plus 2 electrons. And it wants a spontaneous cell, so we're going to, again, be forced to pick on our own which one's going to be the cathode and which one's going to be the anode. So what I'm going to do is switch to over here because I'm going to run out of space too quick. The two half reactions were cadmium 2 plus AQ plus 2 electrons goes to cadmium solid with a standard reduction potential negative 0.40 volts. The other one was tin 2 plus AQ plus 2 electrons goes to tin solid. The reduction potential for that, negative 0.14 volts. So we have to pick which one's going to be the cathode and the anode. The one that's going to be the cathode, the one that's going to undergo reduction, is the one with the higher value. So this one, negative 0.14, is higher than negative 0.40. So this one's going to be the cathode, and this one's going to be the anode. So the cathode, we said, was equals plus 0.26 volts. That part is pretty straight. Pick the one. We want to pick the one to be the cathode that gives you a positive value for E0 cell. If you flip them around, if you pick the wrong ones, you'll get a negative number. So that's obviously not going to be written in the spontaneous direction anymore. We're also told that in this real cell, cadmium 2 plus is 0.020 molar and tin 2 plus is 0.20 molar. Well, let's write it out. Let's write out our cell reaction here. We know the one that's being reduced, because it's the cathode, is the tin. I guess that's AQ. And the one being oxidized, the anode, is going to be the cadmium. So we have to flip the cadmium one. We add these two together. The electrons will cancel. Aqueous, solid, solid. Okay, so the first thing we have is E0 cell. Looking at this equation, when we add them together, we could say that N equals 2. There's 2 electrons being transferred in this particular step. And we could say that Q is going to be the concentration over the concentration of tin 2 plus. We don't worry about cadmium and we don't worry about tin that are solid phase because solids don't appear in equilibrium expressions. So we only have these 2 concentrations we need to worry about. So I think we are about ready to put this all together. We would say that E cell is E0 cell minus RT over NF. No, I went too far there. Long Q equals our E0 cell we said was 0.26 volts. Minus R 8.314 joules per K mole times temperature, which is 298 K, divided by N, which we said was 2, divided by F, which is a constant, 96485 coulombs per mole, times the natural log of Q, which is concentration of cadmium 2 plus, and divided by the concentration of, right, we're right here, over tin 2 plus. And we're given those 2 concentrations in the question itself. I don't think I rewrote them here, but they're on the slide. Bring that back just a second. You can see that we are given concentrations on the slide. So we just use those concentrations over here, and we would say that needs to go away. The concentration of cadmium 2 plus was 0.020 divided by the concentration of tin 2 plus, which we said was 0.200. Notice in that Q expression right here, I left out units. And that's because when you put values into the equilibrium expression, either Q or K, you leave the units out because you're technically putting in activities, which are unitless. So we leave those units out, and then we can run the calculation. And running this calculation, we get plus 0.29 volts. So if you look at that value for the E0 cell, or the E cell, it's actually not that far off our E0 cell. Our E0 cell was 0.26. So under standard conditions, the voltage would be 0.26 volts. By using these concentrations, which are very different from 1 molar, that only changes the voltage by like 0.03 volts. So it changes it by like 10% or so, which is not insignificant, I guess. But, you know, still, it's not like some wildly different value. So if you have an E0 cell that is large and positive, like greater than 1.0 volts, for example, that correction factor will almost never get to the point where it can make that cell non-spontaneous. So those kinds of reactions will go like all the way to almost completion before the battery goes dead. It's not like there's still reactants left for reactions with large positive voltages. Great, so this is good. We can now calculate the E of any cell, the voltage for any electrochemical cell, under any set of conditions that we want, any set of temperatures and pressures. And not only just pressures, but concentrations too. Perfect. There's one other thing that I wanted to mention, which is a weird thing with electrochemical cells that you don't see this when you're doing equilibrium, typically. And this is if you had a cell reaction that looked like this. If you have H plus zinc solid 2H plus AQ goes to H2 gas plus zinc 2 plus. The two half reactions, the two reduction potentials here would be 2H plus 2E goes to H2 gas. And does anyone know what the E0 value for that reaction is? And by anyone, I mean you, not to put anyone on the spot. Value is 0. That's the standard hydrogen electrode. Where the other one was the zinc 2 plus 2 electrons goes to zinc solid. I think the E0 here is negative 0.76 volts. So in this particular reaction, the one that wants to be reduced is the hydrogen because it has a higher E0 value. And the E0 of the cell will be plus 0.76 in the direction that's written. But if you're under non-standard conditions, think about what's going on here. We have a concentration. So let's say this was like 0.5 molar. The zinc we don't care about because it's a solid. We have the zinc 2 plus, maybe 0.1 molar, something like that. But we also have hydrogen gas. And hydrogen gas, standard conditions is 1 bar, but let's say we're at like, I don't know, 0.4 bar. How do we come up with a Q for an equation like this? Well, Q is going to be equal to the pressure of H2 times the concentration of Zn2 plus divided by the concentration of H plus squared. So this would be equal to something like 0.4 bar. Well, we don't put the bar in, we don't put the units in, but they have to be in units of bars where you put them in. I'm going to get rid of that. Times the concentration of zinc is 0.1 molar divided by H plus, which is 0.5 squared. So the reason this is weird is we're mixing pressures and concentrations in the same equilibrium expression, which we normally don't do. Like when we normally do equilibrium constants, we only keep one phase as the relevant phase dominating the equilibrium. But for electrochemical cell reactions, we use both the gases and the concentrations when we're using our Q expression. And there's a couple of reasons for this. One is when you separate it into half reactions, you know, things are going to be necessarily in different phases because they're in different regions of the electrochemical cell. The other thing is when you're doing a cell reaction that involves a gas like hydrogen, it's not like there's a set amount of hydrogen that's disappearing or not. You are constantly bubbling it over the electrode material, so it's constantly undergoing reaction, and so it's always being replenished. So it's not like it can disappear like it would normally do in a reaction that's going forward. So just remember, Q, if there are pressures, use both the pressures and the concentrations when you stick them eventually into this Nernst equation up here. Cool. One thing I do want to say about this chapter is this is a really long chapter, and I didn't put these slides together myself. You may notice a slight difference in style of the slide. The person that did is a electrochemistry expert, and therefore there's like 25 slides of extra stuff at the end of this chapter, which is like cool applications and this and that. I'm very tempted to skip all of that because it's not something I would be testing you on anyway. However, it talks about, you know, different types of batteries and the history of how batteries were developed and all of that sort of thing. We can like just do like a quick, maybe brief run through of some of it, but I don't want to bog down and spend too much time on that stuff when you're not going to be tested on it ultimately anyway. Okay, I did, though, suggest earlier on that there's such a thing called a concentration cell, where you can have the same cell reaction in both halves of the electrochemical cell, but what drives the reaction is a difference in concentration on the two sides. So we have a cell here where we have a silver electrode and a silver electrode, and we have silver plus and silver plus in solution on both sides, separated by our salt bridge. The only difference, the only driving force here is that the concentration is the same on both sides. So it's going to want to proceed until the concentration is the same on both sides at 0.3 molar. This is really no different than any other example you could get, except that when you apply the Nernst equation, the E0 cell necessarily is going to be 0. Because you have the exact same half reaction on both sides, there's going to be no difference in the standard potentials of those two half reactions. So the entire voltage of this cell, the entire driving force for that cell, has to come from this correction piece, which we already said is typically pretty small compared to E0 values for most cells. So if you look at these two half reactions, basically what we're doing is we are going to plug them into this equation. 0 is going to be our E0 cell. So our E cell is 0 minus R times T, n number of electrons that are moving, times F, which is a constant, times the natural log of 0.1 over 0.5, which gives you a very small voltage of 0.04 volts. This conceptually might seem quite different from the previous cells, but it's actually easier because there's sort of less to concern yourself with. You don't have to worry about the E0 cell part because it's 0. Right, so what'll happen is this will move forward. As these two values get closer to each other, as the cell reaction proceeds in the spontaneous direction, eventually the numerator and denominator will be the same value, concentrations are the same, and then you have natural log of 1, which makes the entire cell voltage equal to 0. When E cell is 0, you're at equilibrium, delta G is 0, there's no driving force to go in either direction. Perfect. So another example of the same thing. It's at 9:20 right now. This really is not much different than the one we saw before. Basically, we would say E cell equals 0 plus RT over NF ln 0.10 over 1.00. And if you put these numbers in, I have it here somewhere. Very small voltage of 0.030 volts. Great. I didn't go through that in much detail, but we are pretty much out of time. And we're also kind of completed the chapter already. I just wanted to kind of get that done last day of the week. And so what I'll do is I'll put up an assignment based on the latter half of the Electrochem chapter. And I'll send into my email, make it clear how this is going to work in terms of it being optional or mandatory. If you do have Calc and Bio midterms next week or any other midterms in addition to that, very best of luck. And I hope you all have a great weekend and have a chance to relax a bit too. Great. Stop sharing. We're going to stop recording.